Hey there, Namaste, welcome to my YouTube channel. I'm Prabhat Ale. So in my previous video, we have talked about the security issues in face recognition system, and we have also covered about the face anti-spoofing system, right? So we have also seen the demo of face anti-spoofing system in that video, but in this video, we are going to build the live face anti-spoofing system from scratch, right? So in this video, we are going to train our anti-spoofing model, and then we are going to integrate that face anti-spoofing model into our OpenCV applications, right? So without getting any further delay, let's start our video by understanding the workflow of our system with the help of flowchart.
So here we have two possibilities in face anti-spoofing system. One is a real face and a spoof face, right? So those faces are forwarded to the face detection process. So in the face detection process, the facial region is detected and extracted, and those extracted images are resized into 160 by 160 pixels, and those resized faces are forwarded to the liveness model or the face anti-spoofing model. So the model is capable of figuring out whether it comes from a real person or a fake person. So if that comes from a real person, then it labels as real, and if it comes from a fake person, then it labels as spoof, right? So that was for this theory part. So now it's time to code and finally build this system. So whenever we are working on any computer vision problem, the first step you need to consider is gathering the datasets for training your model, right? So you don't need to worry about the datasets. I will be providing these datasets. So I have uploaded these datasets in my Google Drive. So here's the zip file to my datasets. So you don't need to worry about this link. I'll be providing this link in my YouTube description. You just open this link and then come up to this page, and then add this shortcut to the drive. Okay, so by adding this dataset shortcut to your drive, you will be able to access these datasets from Google Colab, right? So now let's take a look at the datasets that we'll be using to train our system. So here you can see that our dataset is split into train and test. So let's take a look at the training datasets. So inside the training datasets, we have two labels, that is real and spoof. So these are the labels that our model is going to credit. So let's go inside the real directory to see what's inside it. So here you can see the directories with the name of the person. So let's quickly open any one of them. Okay, so these are the real images of a person. So here you can get the idea of how our real images would look like. So let's quickly see how our spoof images would look like. So here so for this you have to go into the spoof directory and choose any one of the directory. So here these are the spoof images. So you can get an idea of how our spoof images would look like. So now let's head on to the step number 2, in which we will set up the workspace for training our anti-spoofing model.
So for training our anti-spoofing model, we are going to use Google Colab as a workspace. So the first step we are going to do is that we are going to access the datasets that we have uploaded earlier in Google Drive into this workspace, right? And then we are going to unzip that data and do data preprocessing part. So let's do this. So I've already written some amount of code here. So the first block of code, what it does, it just connects the Google Drive into our workspace, right? So I'm going to choose the drive. So after choosing all those things, then we are going to copy this authorization code, okay? And then we are going to paste it over here. So the important thing to note is that you are going to connect with that Google Drive or with that Google account where your dataset is located, right? So in the second step, we are going to copy our antispoofing.zip file into our root directory, that is this /content. And then in the third step, we are going to unzip this file. Yes. So here you can see, after unzipping this file, this dataset is finally here. So now we are all set to do the data preprocessing part. So in the data preprocessing part, so we will be following our 4-step principle. So in the first step, what we are going to do is we are going to create a new directory structure for our databases. Okay, So then in the next step, what we are going to do is we are going to copy all the images from our original directory structure to our new directory structure, right? In the third steps, we are going to explore the datasets. That means we are going to see how many training images and how many testing images are there in the datasets. And finally, we will visualize the datasets, right? So let's head on to step number 1. So in step number 1, we are going to create a new directory structure for our project, right? So previously the directory structure was like this. So we have a root directory at the beginning, and then inside that root directory we have train and test, and inside train and test we have real and spoof, right? You used to see here real and spoof in both train and test, and inside that real and spoof we have the directory belonging to a specific person, and inside that directory we have the training and testing images. But we want our directory structure such that we have the training and testing images just inside the real and spoof directory. So for that purpose we are going to create our new directory structure, right? So for this, what we are going to do, we are going to write some codes. So I've already written some of the codes, so I will explain it. So in this code we are just storing the paths of our previous directory structure into some of the variables, right? So now in our next cell, what we are done is we have created a new directory structure, yes, by using os.mkdir command, right? So then we have just provided the train directory and test directory paths to train underscore dot and test underscore dot variables. So now this creates our new directory structure. So let me show you how the new directory structure. So here, this is my new directory structure, anti-spoofing underscore dataset. So inside anti-spoofing underscore datasets we have train and test, and inside train and test we have real and spoof, right? Yeah, you used to see, and inside real and spoof there are nothing right now. So now we want to copy the images from our original datasets or previous dataset structure into our new dataset structure. So let's do it in step number 2. In step number 2, we are going to copy the images from our original datasets into our new dataset structure, right? So for doing this, we first need to import all of the libraries that will require for this task. Okay, so for doing this, so I'm going to run this cell. So these there are 4 libraries that we will require for doing this task. So first is Sutil, next one is NumPy, third one is Matplotlib, and next one is OpenCV, right? So in the next step, we have written a function to copy the images from one dataset to another dataset, right? So this is the function that will do the task. Okay, so don't worry about these functions. I will upload this notebook file in my GitHub and provide you the GitHub link in my YouTube description. Okay, so let's run this function for now. Okay, so after defining a function, so what we need to do is we need to call a function, right? So this function is taking a parameter called data underscore directory, which is using the parameter is dataset underscore dot. So here we have mentioned this dataset underscore dot equals to final underscore anti-spoofing. So that means we are going to copy these datasets into these datasets, right? So let's run this. So let's call this function. So here we are running this function. Now we are all set, so you can just look at the images now, right? So there are some of the test images. Okay, it is taking some time. Here you can see all the images are being copied from the original dataset into our new dataset. So now we are all set for step number 3. So in step number 3, we are going to do the data exploration part. So let's head on to step number 3. So in step number 3, we are going to do data exploration, right? So in data exploration, we are going to see how many of images comes from training dataset and how many of them come from testing datasets. Similarly, we are also going to check how many of training images comes belongs to real category and how many of training images belong to spoof category, similar with the testing datasets, right? So here we have two categories, that is real and spoof. So these are the categories that we want to predict, right? So these are the outcome variables. So I'm going to run this cell, and this is the code that we will run to see the distribution of data. So let's see what is the distribution of data. So here you can see, so there are a total of 4,220 training images, out of which 2,102 images belong to real directory and 2,118 belongs to spoof directory, right? So similarly, there are 951 testing images, out of which 477 belongs to real directory and 474 belongs to spoof directory. So by looking at the distribution of data, we see that the data set is not skewed. That means the data set is balanced, right? So now let's head on to step number 4, that is dataset visualization. In step number 4, we are going to visualize our training datasets and testing datasets, right? So for doing this task, we have implemented two functions. So the first function is get_image and next one is visualize_datasets. So first, let's understand the first function, right? So in our first function, we have provided two parameters. So first one is data_dir and second one is number of samples. So let's understand the interpretation of this function with the help of example. Suppose we provide the path of our training datasets in data_dir and number of samples equals to 25, then this function returns a list containing 25 images from real category and 25 images from spoof category of our training datasets, right? So now let's understand the second function, visualize_datasets, right? So visualize_dataset function also takes three parameters. First one is images_path, second is rows, and third one is columns, right? So it takes the list of images and display them in rows and columns, right? So suppose we take a list containing 50 images and then we want to display our image in 5 rows and 10 columns, then this function will do the task. So let's see the interpretation of this function by running these functions. Okay, so let me run this, and again let me run the visualize_dataset. So now we'll call our first function get_images, which will return a list of 50 images, out of which 25 belong to real category and 25 belong to spoof categories, right? So here you can see. So after this, we are going to call our second function visualize_datasets, which will visualize our training datasets. So here you can see these are the training images. So we have displayed these training data sets with the help of matplotlib library. So here you can see the images, and below there's a label indicating the category of each image. So these are all the real images. So you can go below to see our spoof images, right? So the real images belong to the real person and the spoof images belong to the images that are taken from photos, right? So now let's visualize our testing datasets, right? So here you can see the testing datasets. So at the top we can see the images belonging to the real category, and at the bottom we can see the images that belongs to spoof directory. So this completes our data preprocessing phase. So now let's head on to the next phase, that is model preparation, right? So in model preparation we generally create a model that is appropriate for anti-spoofing system, right? So in model preparation also we are going to follow some of these steps, yes, for preparing our model. So number one step is that we will choose the appropriate framework and import the necessary libraries, right? So that means, so there are lots of frameworks that we can train our network on. We can use TensorFlow, we can use Keras, we can use PyTorch, and there are other libraries or frameworks as well to train our deep neural networks, right? So if we choose Keras, then we have to import all the necessary libraries related to Keras, right? Similarly, if we choose TensorFlow, then we will have to import all the necessary libraries that are related to TensorFlow, right? So in step number 2, we will do load the datasets and perform image augmentations. So we generally perform image augmentations to increase our datasets and to prevent our network from overfitting, right? So in our third step, we will do the model selection, right? So choosing the appropriate model is very vital, right, because it helps to prevent our network from overfitting as well, and we have to choose the model such a way that it will not be overfitted and it will achieve the good or greater accuracy, right? So next one is compiling our model. So we have to compile our model before training our model, and then in the last step we are going to set our model set point. So that means, so after training we are going to store our model learned model weights and parameters at a checkpoint, right? So that we can see we can see the accuracy, and we can store our models after every epoch, right? So now let's head on to step number 1. So right in step number 1, so we are going to choose the framework and import the necessary libraries. So here we have decided to stick to the Keras framework because it is very easy to build a neural network in Keras framework, and it is preferred by different data science to prototype solutions quickly as well. So we are also choosing Keras framework, right, because it is easy and we can create a prototype very easily and very fastly, right? So then after choosing the Keras framework, we have to import the necessary libraries, right? So here we have import all the necessary libraries that are associated with Keras for doing the training. Now we are going to run this. So now in step number 2, what we are going to do is we are going to load the datasets and perform image augmentations, right? So here, so we have two different data sets, that is one is train underscore data generation and second is valid underscore data generation, right? So we are going to apply different types of augmentations, like we are going to increase and decrease the range of the brightness. We are going to do different kinds of rotations. We are rotating our images at a degree of 30 degree, right? This will be random, and it is chosen in such a way that the maximum rotation range is 30. Yes, the minimum rotation range can be 0 to 30, and then width shift range equals to 0.2, in which we are going to shift our image widths, and height shift range, similarly we are going to shift our height of our image, right, that is 0.2, and fill mode equals to nearest, and we are also using CO range equals to 0.2, zoom range equals to 0.3, and this is the most important part. We are going to rescale our image because by 255, because as we know, we are in neural networks, what we are going to do is we are going to use gradient descent algorithm, right? So for gradient descent, we need to normalize our data sets, right? So for normalizing our data sets, we are using rescale equals to 1/255. So these all augmentations are done for training datasets, but for validation datasets we are not doing any different kinds of augmentations. We are only rescaling. That means we are only normalizing our image. Now let's run this part also. So now we are going to choose our target size is 160 by 160, and we are using color mode equals to RGB, and we are doing binary classification, that is real or spoof, and we are using a batch size of 25, and we are shuffling our training datasets, and in this way we will generate our training data generator. And we have here, we can see we have 4220 images belonging to two different classes, and similarly we are going to load our validation generator. So here you can see we have 951 validation images belonging to two different classes. So now let's head on to step number 3. In step number 3 we are going to choose our model. That means we are going to select our model and perform transfer learning also. So in step number 3 we are going to select our model and perform transfer learning. So here we are using MobileNet version 2 model. So why we are choosing MobileNet version 2 model? Because it is very lightweight and it provides faster inference during the real-time detection, right? So we are choosing MobileNet version 2 model, and we are using the pre-trained weights of ImageNet datasets, and we have not included the top layers, and we will provide input set of 160, 160, 3. So let's run this. And we have set mobilenet.trainable equals to false, so that means we are not training our upper parts of the network, right? And here we are using the terminology called transfer learning. So we are using the technique of transfer learning. So that means transfer learning is a technique in which we transfer the knowledge that the network has learned from the previous tags to our new tags, which is similar, right? So this so we are transferring the knowledge of the network that has learned from ImageNet datasets to our anti-spoofing datasets, right? So we are not training the upper parts of the network, so we are setting it as false. So now what we are going to do is we are going to create an output layer, and we are going to create a prediction layer, right? So here we are creating output layer equals to flatten. So we have to flatten our networks, and then we are multiplying the flattened output by MobileNet output layer, right? And then we are using the dropout, and then we are multiplying it with output. So what does dropout do? So dropout generally helps to prevent the network from overfitting. We are using dropout of 0.3. That means 0.3 that means 30% of neurons are turned off during training. That means all the neurons will not be turned on. That means all of the neurons will not be take part in the activation, right? So next, then we are going to use a dense layer, and we are creating a units of 8, and activation equals to rel. We are using rel activation unit, and then we are multiplying with the output, right? And then finally we are doing the prediction. So in prediction we are only choosing one, either real or spoof. So we are using one layer, and activation equals to segment, and then we are multiplying it with output, right? And then let's run this cell again. So now we are going to what we are going to do. So we are going to create our model, so in which we will take the input from MobileNet data input and outputs from prediction. That will be our output, that is one layer, yes. And then we will summarize our models. So we are run here, so you can see this is the summary of our model. So we have this is the architecture, or this is the summary of our model. So now let's head on to the next step, that is compiling our model. So now let's compile our model. So for compiling our model, what we need to know is we need to know about the loss function that we are going to choose, right? So since we are going to classify whether the image is, or whether the person in the image is real or spoof, so we are choosing binary entropy loss, and then we are choosing Adam optimizer, in which we have set our learning rate as 0.000001, because we have choose this is small learning rate because we are doing transfer learning. Our network has already learned different things from ImageNet, and so we are just adjusting our weights. So for adjusting our weights, yes, we just need to set learning rate is very small, yes. And then we have to choose beta and beta 2 and epsilon. These are other hyperparameters that we need to provide, and we are using the matrix as accuracy, right? So now let's run this model and compile our model. Okay, so it is successful. Now let's head on to step number 5. In step number 5, we are going to set our model checkpoints. So in our model checkpoints, what we'll do is we are going to store all the model weights, yes, in our different locations, right? So that we can download that model and we can use it for inference, right? So after every epoch, the model weights are stored in a model checkpoint. So for that purpose, we are creating a new directory called model_weights here. So let's create a new directory here. So here you can see, yes, model_weights has been created. So inside the model_weights, we are going to store all the pre-trained weights of antispoofing model, and then we are going to download from here, yes, after it has been trained, right? So now we will run this model underscore checkpoint variable. So we will save our best model, that means, and we are only saving our weights. We are not going to save the architecture, right? And we are going to monitor our validation loss. So whenever the validation loss decreases, then we are going to save our model. If the validation loss does not decrease, then we are not going to save our model. And this is the name of this will be the name of our model. Yes, final year project. Yes, anti-spoofing model epoch, and then we are going to store it in S5 format. So now let's run this again. Okay, so now we have done it, and now finally we are ready to train our network, right? So for training, we are providing a variable history equals to model.fit underscore generator, and we are providing train generator, and steps per epoch equals to train underscore generator dot samples divided by 25. So this is validation data equals to valid underscore generator, and validation steps equals to valid underscore generator dot samples are divided by 25, and we are choosing the epochs 75. Let's choose the epoch of 100, and we are using the callbacks as model checkpoint, not early stopping here. Okay, I'm sorry, we are going to remove early stopping, and then that's all set. Now let's run this, and now after running this, our network will be trained, and we will wait until the network gets trained. Yes, so here you can see we are in epoch 1 by 100, so we are training up to 100 epochs. So now the model training will start very soon. So here we are using Google Colab because Google Colab offers a very high-end GPU, so that we can train our network in the GPU, right? So it is still taking some time. It is figuring out all those things. It is loading those loading data sets. It is doing rescaling. It is doing different types of image augmentations. Yes, so it is taking some time. So don't worry, it will get started very soon. So after start, it will start training, and then after it will take some amount of time to train up to 100 epochs. Yes, now here you can see our model has started training, and we have already gained an accuracy of 52% in our first epoch. So let's fast forward the training, and then we'll come back after our model is being trained 100 epochs, right? So now we are halfway through the model. You can see we have already achieved an accuracy of 90 to 93% on training accuracy, and 95% validation accuracy in 50 epochs. So we still have 50 epochs left to be trained. So let's see how much accuracy do our model achieve at 100 epochs. I think we will get above 95-96% accuracy at the end of 100 epochs. We have already achieved 94%, around 94% training accuracy, and around 96 or 95% validation accuracy. So here you can see that the model has already been trained for 100 epochs. So we are able to get around 96% training accuracy and 97% is validation accuracy. That is very good model, right? So I'm going to show you all the model checkpoints that we have got. So you can see that we have stored the model checkpoints in model underscore words directory. So these are all the model checkpoints that is stored in this location after every epoch, right? So if the validation loss decreases, then only we were able to store this model in this directory, right? So our best model is 97% validation accuracy at 97 epoch. So what we are going to do is we are going to serialize our model. So that means we are going to store our model, save our model, and use it for inference, right? So for that purpose, we first need to serialize our model architecture in a JSON file, right? So for this purpose, I'm going to serialize our model in a JSON file. So okay, I'm just writing is final year antispoofing model.whilelet.json, and then I'm going to run this file. So after running this file, we will see something like this here. you can see we have, this is the serialized model, so you can see here also. So this is the JSON file, right? This here we have saved all the model architectures, right? So whenever we are going to use our model for inference, we need model architecture files and the model weights file, right? So that's why we are saving architecture files. Now we are going to save our model files. So now what we need to do is we just need to download these two files, right? So that we could use it for inference later on. Yes. So we will be use the inference in our local system. So we are need to download this file. Okay. So we again downloaded this best weights file. So it is of 9 MB. So it will be downloaded. So until it gets downloaded, let's look at the graphs, look at the training accuracy and training loss, validation accuracy plots in a graph, right? So here you can see training versus validation accuracy graph. So this is the training versus validation accuracy. Yes, this blue line is the validation accuracy and this green line is the training accuracy. You can see that model is continuously improving. I think if we train it for further epochs, it will again learn. So but here 97% validation accuracy is enough. So now we can also see the training loss versus validation loss. You can see, yes, the green line is the training loss and the blue line is the validation loss. So now let's see, let's check the results. Now let's check our prediction results. So for checking our prediction results, what we are going to do is that we are going to load all the images from our validation data sets, and then we are doing the predictions, right? And we are doing the predictions and storing all those predictions in a predictor dictionary, right? Okay, so let's run this function called checkfetch. So now we are going to call this function and we are going to provide a path. So this path will be validation directory path, and then we will check against categories 1. So that means real spoof, means we are checking all the spoof images that is inside the validation directory, and then we will run this, and after running this we will get a dictionary. So here we can see valid_dir is not defined. So what is valid_dir? I think we have to provide valid_dir here. So let's see. Oh, test_dir. So we need to give test_dir. So we have given the name test_dir in place of valid_dir. So here we need to give this directory path is test_dir, and then run it again. So then it will take some time and you will see the results. So we can run this part as well, test_dir. So after running this file, what we'll get a dictionary indicating the prediction results. Suppose we have 600 images in our spoof directory, right? So out of 600 images, if our model predicted yes, 19 is real and rest is spoof, then we can see here. So here we can also see, so there are total 455 plus 90, that is 474 images. So out of 474 images, spoof images, our model has predicted 455 is spoof, which is correct prediction, and 19 images spoof, this is a wrong prediction, right? So here again, so out of 471 plus 6, 477 images, it has predicted 471 is real and 6 is spoof. So our error is 19 plus 6, right? So 19 plus 6 equals to 25, right? So this is our error. So we will calculate the percentage upon, and then we will go with 19 plus 455 plus 471 plus 6. These are our total images, and then we are going to multiply it with 100 and then run this. You will see the accuracy. I'm sorry, this accuracy is okay. So we can go here. Yes, so we can see this is 2% loss. So we can see this is our loss percentage. So that is 2.62% is our loss. When we subtract it from 2.62 at it, so then we will get this as our validation accuracy. So we have obtained around 97.37% accuracy in our validation model. So here we have already stored our weights file and architecture files, which we will use for inference. So that's much for the training part, this notebook part. So now we'll head on to the deployment phase, in which we will do a live the deployment part, in which we will be able to deploy this anti-spoofing system through the help of web camera and OpenCV. So without getting any further delay, so let's quickly jump to the deployment section. So now we are in the last phase, and we are going to deploy the anti-spoofing system in our local environment. So for doing this, we are going to create a new folder for our project and name it as Antispoofing_system and press enter, and then navigate to this directory and copy the path, right, and then open Anaconda prompt. Okay, so now then change the working directory. Okay, so now we are inside the Antispoofing_system, that is our project directory, right? So next thing we need to do is that we need to clone this project repository, right, into our local environment, right? So these are the project files for a face anti-spoofing system. So we just need to copy this path or URL and then come into this Anaconda prompt and just type in git clone and then paste the URL and then press enter. Okay, so it will take some time to clone all those project files into this new project directory. So okay, the project files has been cloned successfully. So now you can go here and then you can check, yes, the project files has been cloned successfully. So now what next thing we need to do is we need to go over the downloads folder or wherever your download files are stored, right? So you just have to think earlier, you just have to remember earlier we have just downloaded two models. One is mobilenet.json architecture file and the weights file, right, so that we can later on use it for inference. So what we need to do is we just need to cut this and move these two model files into anti-spoofing models and then paste it over here, right? Okay, so now let's again open Anaconda prompt and then you can see, and then let's change our working directory to this directory. So you can see these are all the project files that we need to for this anti-spoofing system. So here you can see liveness net_net.py is the main file that we are going to run for, yes, doing the inference on face anti-spoofing system. Okay, before running this file, we just need to download some of the requirements for running the system or project. So let's see what are the requirements here. Okay, so I'm going to open an interpreter, a equals to open, and then I'm going to go with requirements.txt here, and then b equals to a.readlines. Okay, b equals to a.readlines. Then I'm going to go print b. Okay, you can see that we have two dependencies. One is TensorFlow 2.5.0 and then OpenCV Python 4.4.0. So now we need to install all those dependencies. Okay, so for installing those dependencies, we first need to create a virtual environment, right? So you know how you can create a virtual environment in Anaconda. So for creating a virtual environment in Anaconda, we just need to type in conda create -n and the name of virtual environment, let's say anti-spoofing. Okay, and then choose the development environment, that is Python 3.6 and press enter. so it will take some time to create a virtual environment for you. Just be patient. So here it is collecting all the package metadata. So okay, after some time it will ask whether to proceed or not. Just type in Y and press enter. So then it will download all those environment like Python 3.6. it will download Python 3.6 and other packages that is necessary for building the virtual environment. So it will take some time. So okay, so it has already created a virtual environment so for us. So now we need to activate this virtual environment. So for activating this virtual environment, we just copy this command and press here and then press enter. So now you can see our virtual environment has been activated. So now we can take the directory and now we can install all those requirements inside our virtual environment by just typing a command pip install -r requirements.txt and press enter. So this will take some time because it is going to download the OpenCV 4.4 and then 4.4.0.40 and TensorFlow 2.5 from the network. So you must have a good internet connection, yes, for running this for installing those requirements. So if you do not have internet connection, then connect to then it will not work. So let's wait until all those installations are done. So after all those installations are done, then we'll open our main file in our Visual Studio Code and then we'll make some adjustments or edits and then we'll run this project file. So now you can see that all the requirements have been installed successfully. So now it's time to run the project finally. Okay, so for running this project, we first need to go here and then choose our main file, which is Liveness Net. So let's open this file with the help of Visual Studio Code. Okay, so it will take some time. So here, so these are the program files. I have already written this code. I will provide this helper script in my GitHub. So the link of the GitHub file will be provided in the YouTube description. So here I'm going to explain each and every section of course that is written here. So in the first 5 lines, so we have just imported all the necessary libraries that will be required for this anti-spoofing system, right? So then the rest of the course, then for the rest of the course, so we need to understand the workflow of our system, right? So how our workflow of the system is explained earlier. So we know first the web camera got initialized, and then what we do, then the face detection algorithm is loaded up, and then the face is detected, and then we resize into 160 by 160 pixels, and then we do some image processing techniques, and then after applying some image processing techniques, we just feed that model into the anti-spoofing model, and then this anti-spoofing model does the prediction on that image, right? So and if that predicted confidence is greater than 0.5, then we label the confidence, we label the prediction result as spoof, yes, and if the prediction confidence is less than 0.5, then we label the prediction confidence as real, right? So all these things, so we just need to know. So for this purpose, so here we have loaded this face detection algorithm, that is OpenCV R cascade classifier in face underscore cascade variable, and then we have loaded this JSON file, right? So this JSON file has been loaded, right? We have provided the appropriate we need to provide the appropriate path here, right? So we just need to do, so for this path we just need to provide the appropriate path here. Okay, we have provided the appropriate path, and then it is loaded up. So then we have to load our model weights, right? So for loading our model weights, we just need to provide this path as well, right? So for providing this path, so let's predebit, okay, and then all those models are loaded. So actually there are two models. So one is face detection model, that is from OpenCV's R Cascade classifier, and then our pre-trained models. So our pre-trained models consist of two things. One is weights file and the configuration file or architecture file. Architecture file is in JSON format and model weights file is in H5 format. So we have loaded everything up. So now our workflow starts from here, right? So first though, it will capture the webcam. Yes, it will start the webcam, and then from webcam we read every frames, right, and then convert it into grayscale, right, because OpenCV's face detection algorithm works on grayscale images. So for that, yes, then after on is detected faces, we just extract the frame that is related to only facial region, and then we resize that facial region into 160 by 160 pixels. Then we do some image processing operations here, and then we feed that pre-processed arrays or pre-processed face into our models, and then the model does the prediction. So if that predicted confidence is greater than 0.5, then it is labeled as a spoof, and if that predicted confidence is less than 0.5, then it is predicted as real, and then we just draw a bounding box around our facial region, and then we show our frames, and then we finally close it. Okay, so that's the code. So now let's run this code and test our inference. Okay, so for running this, so I'm going to copy this file, and I'm gonna come over here and Python, and then I'm gonna paste this command and then press enter. So it will take some time, so just be patient. So finally you can see that the program is running now. So it has detected my face and created a bounding box around my faces, and at the top of the bounding box it has created a label or printed a label called real, so which indicates that the model has identified my face as a real face. So now let's try to spoof the system and see how the system behaves. Okay, so I'm going to show the picture of me in my mobile. So let's see how the system behaves to the printed photo or to the mobile photo. Okay, here you can see that it has again created a bounding box around my facial region, and it has printed a label at the top called spoof, so which means that it has identified this face as a fake face, so that the system is working perfectly fine. So let me close this. So that's was for this video. So in this video we first train our own anti-spoofing model on our own data sets, and then we download the pre-trained weights and architecture files, and then we just load it up and then do the inference during on real time using OpenCV and Python. So I hope you guys like it, and see you guys in my next video. Until then, stay safe and keep learning.